Hi, Stephen here with a guide to selecting the correct cross-sectional area for your cable. A common software approach is to use an algorithm to calculate the correct size. These tend to be simple. For example, look up the correct current capacity of the table and increase the cross-sectional area if necessary for voltage drop. In many instances this approach does not work. For example, it may be that either 300 mm squared, 240 mm squared or 2 times 120 mm squared can all be used, and the best one depends on project factors. Additionally, reliance on simple algorithms can result in over-reliance in software by engineers, leading to fundamental mistakes. We take a different approach, recognizing the knowledge and experience of the engineer in deciding on the correct CSA and viewing our software as a tool supporting the engineer by providing easy and quick analysis and performance information. To give the approach a name, we use Engineer First, and I will demonstrate how this works. To start, I will create a new cable so that I can work through some scenarios. Most settings I will leave at the default values, but change the current to 600 amps and select an MCCB for the protective device with an electronic trip unit. Select an armoured single core XLPE cable and leave the CSA selection for the time being. For the sizing standard and installation, I will use BS7671 with the cable in free air and laid flat on the ladder. Returning to the cross-sectional area and our engineer first approach, we don't pre-fill a selection and require a CSA to be selected. If we did pre-fill, it would be 300 mm squared, and you will see why in a second. It may be that the user knows his cable CSA and is using the application to verify the selection, or alternatively want the application to suggest a value. My thinking is that 240 mm squared is about right. However, if I wanted a suggestion, I can just choose the smallest available CSA, in this case 50 mm squared, and wait for the calculation to update. The top section of the calculation is current capacity and is showing a red traffic light, indicating there may be a problem. It is also suggesting 300 mm squared, which is the value you would arrive at using the BS7671 tables and derating factors. Now I can change the CSA to 300 mm squared, let the calculation refresh, and we have the first potential cable size. I suggested 240 mm squared is possible, and we can quickly check that by changing to 240. The calculation has been refreshed and is red indicating a possible issue. However, looking at the current values, the rated capacity of the cable is 624 amps, the design current is 630 amps based on the protective device rating, and the cable current is only 600 amps. Given this distribution, it could be argued that the cable is adequate as it stands, particularly as the conductor temperature is only 85 degrees. We can further refine the cable by, for example, changing the installation from laid flat to trefoil. As we can see, this gives a good result. Another possibility is to look at the protective device setting. Changing back to flat formation, we can set the overcurrent protective device rating to say 620 amps, and the calculation refresh once again shows the cable is good. We could also look at the possibility of 120 mm squared cables in parallel. We can quickly run that scenario. And the cable looks good. In fact, it looks like we could use 2 times 95 mm squared. Whether to go for 300 or 240 or 2 times 120 or 95 mm squared depends on the preference of the engineer and any given project. Most projects looking to reduce the initial capital cost are likely to select 240mm². If the engineer wants to be a little more conservative, he could go for 300mm². Additionally, a 300mm² cable has lower losses and operating temperature, possibly resulting in a lower life cycle cost and longer life expectancy. If the cable containment restraints are tight and bending radius is an issue, it may be worth considering the 120 or 95mm² in parallel. Hopefully you can see by now how easy and quick it was to run various scenarios and develop several CSA candidates, and that insisting there is only one right answer is not always the case. Engineer preferences and specific project requirements play an important part. While I've concentrated on current capacity, voltage drop or fault rating follow the same process. Run your scenarios and decide what is best. This is all I wanted to go through today, so I do hope you found it a helpful demonstration on how you can use the application not only to find the correct cable size, but look at various alternatives. And if you haven't tried our application, you can do so by visiting myCableEngineering.com, registering as a user and gaining a free trial to check if the application is right for your needs. Thanks for watching.